everyone. Welcome to the first ever series on this channel for HLIB Chemistry, and to the first episode of this course where I will be trying to explain best what I've learned in school and just to help you guys understand how I really think about these units in chemistry and how I understand them. So today we will be talking about random error and significant figures. Most of this will be a review from grade 10 if you've already taken chemistry in grade 10, part of the science unit. And we will be adding a few terms and basically a new method of calculation. So the first term to be attentive to is repeatability. So what does it mean when something is repeatable? Well, intuitively, I guess it could mean being able to redo something and produce the same result. And that's the same thing in the context of science. It's basically an experiment is repeatable when you can do different trials and arrive at the same result. Namely, this is only between yourself. So let's say that you take a brush and put it in paint bucket A, and you find that after you do so, and in using this brush, you find that on the canvas it produces red paint. If you do this once, and let's say you got red, but the second time you got green, and then the third time you got pink, and basically just every time you do it, you get inconsistent color. What this means is that your experiment is not repeatable. You're not able to personally repeat what you've done, and the first ever time you've done it may have been a fluke or something just wrong happened. So basically, intuitively, doing multiple trials multiple times promotes precision, as you're able to confirm that you're actually arriving at the same result every time. Now let's talk about reproducibility. This is the same thing as repeatability. However, it applies to more than one person. So let's say I take paint bucket A, and every time I use the brush, I get red. But let's say I have a friend, and let's say every time he uses the brush, he always gets green. This means my experiment is irreproducible. My bad. That is really bad because it means that for some reason our results are different. Perhaps the paint I used and the air quality in my room was off or something, but it's really hard to tell just by knowing these few conditions and facts. However, we scientists generally want something to be reproducible. Let's say you found the first semiconductor, however, only you can produce a semiconductor for some reason and no one else is. Well, it might be, since others can't really reproduce your experiment, they might say that your experiment might have been fraudulent, or maybe the steps you laid out were incorrect in the paper you wrote. So what we want is reproducibility. Basically, multiple people can arrive at the same results and conclusions performing the same experiment. And this helps us confirm that something actually has happened and something can happen. So next, we have precision and accuracy. Now, most of you have probably already seen this in grade 10. However, we have the four targets, and just for the sake of um, refreshing the topic, I will explain this once again. Basically, this target, as you can see, is an example of low accuracy and low precision. You can tell that the difference between the dots is inconsistent, and that none of these are near the center. Basically, uh, The closer you get to the bullseye, the more accurate your experiment is, and the closer the dots are together, the more precise. So you can see this in the next diagram where all the dots are bundled together. This means that all the dots are basically this means that your experiment was very precise, as through multiple trials you arrived roughly at the same destination. However, this is not accurate, as you can see, as it is not really approaching the center. And there are areas that we will talk about that account for these scenarios. The next one we have, as you can see, is this one's kind of hard to understand, at least for me. So this is an example of high accuracy and low precision. So we can see that all of the dots, they are near the center. However, they are not near the same area. They are spread out around the target in a fairly weird way, and they are not bunched together. So basically, this experiment has low precision, as when doing the results, let's say maybe this side is 1, this side is 2, this side is 3, and this side is 4, you're getting a wide range of different results. The last one is fairly obvious. It is high accuracy and high precision. The dots are all bundled together and they're near the bullseye. So there's one more term we have to talk about that you might have learned in grade 10, and that's the literature value. This literature value is basically the accepted value of an experiment within the scientific community. So let's just say, perhaps you might not know this yet, but the percent composition of water, H2O, is always going to be the same, meaning that if the closer you approach the percent composition of water, the more accurate your experiment is. So we have two new terms that a lot of labs use, and this is very important towards, as stated before, the labs, and especially for the final IB exam. So the first term, random error, is basically the same as low precision, but maybe high accuracy. So it's basically the irreproducibility and basically replicating measurements, and this affects the precision of the result, which is why precision is written here. Systemic error basically is things to do with accuracy. So this is basically when your experiment results differ from, let's say, the literature value. Maybe, but however, they're all precise. So this affects accuracy. So, looking back at these diagrams, random error would be this diagram, as there is high accuracy, however, low precision. And systemic error, oh my, that's the wrong. Systemic error would be this one. There's high precision. There could be low, but usually it's like this. But there is low accuracy. Usually, if you have both the accuracy and the precision off, you're probably doing something wrong, or there is a lot of things that need to be improved with the experiment and the tools related. So speaking of what to improve, for random error, what we want to improve is the precision of the instruments. So let's say you have a graduated cylinder. Basically, as we will later talk about with significant figures, something like this, a graduated cylinder like this compared to one with markers in between, meaning a more precise measurement, will result in less random error. For systemic error, what we want is a better procedure or a better methodology. What happens in systemic error is that there's one thing that messes up the entire experiment and causes every value to be shifted. So let's say I have a dog and I have maybe a happiness rating. This obviously does not exist in the real world, as it's too complex to really measure the happiness of dogs on a scale of 1 to 10, 0 to 10. However, let's just say in this world, our accepted literature value for when a dog is walked is 8 happiness. So let's say I decide to walk my dog every day. However, let's say I also, because I go outside and walk this dog, I forget to feed the dog. And let's say every time after I walk my dog, the happiness rating is a 3.1, 2.9, or maybe something like just a plain 3.0. My values are precise in this way, as I did the same thing every time. However, compared to the literature value, it is off. So the fault in this experiment is my methodology. I should feed my dog too in order to allow for a fairer experiment. However, as you can tell, sometimes maybe the food we feed can be bad or good. However, just for reference, imagine it's fairly standard for dogs just to eat the same food and they're happy every time. So let's now talk about measurement. So in science, we frequently use significant digits. Basically, this is basically a number where this digit is uncertain. Basically, in this experiment, we get two certain values, so we know that 3 is definitely a part of the value, point 0.3 is part of the value, but 0.05, we are not sure about that. It can be 0.4, 0.04, or 0.06. So we say that this is the uncertain number. So how do we know which one is uncertain? Well, in later experiments, you see that some instruments, like a volumetric flask, might already tell you the uncertainty or the significant digits. However, let's say you're measuring something yourself. So let's say I have maybe a bone. Let's say that bone starts here. So if you were to guess, like if I were to guess as well, I would say this is maybe about 2.5, and let's say the suture is in centimeters. We know for sure that 2 is the right number, as it's certainly not past 3, but it's past 2. However, we don't know if this is really 2.5. It could be 2.4 or 2.6. So we say that this is the uncertain digit. However, let's say we have markers now. And let's say we can say that for confidently that this is 2.4. Well, since we have two certain digits, we need another uncertain digit. So I can guess 2.41 maybe. I can't guess 2.409 or something because I don't know if 0 is certain. There is no way to verify that we are in the range of which 0 is the floor and a different number is the roof. So, how does this factor in to precision and accuracy? Well, we have a thing called absolute uncertainties, and this is basically a range. So, looking back at this ruler, the first thing to know is that the uncertainty, or basically the error, uh, in this measurement, is one half the value of the increment of the measuring device. Because let's say that for some reason we're offset here, maybe, or let's say that something happened and I just read it wrong. This absolute uncertainty basically adjusts to basically make my experiment more precise. So let's say the literature value of something was 12.01, which is maybe around the molar mass of carbon. But let's say in my experiment, I got 12.00. However, the device I used was not very precise. From this is the absolute uncertainty, and from this I can deduce a range of where the actual value may lie. So in this particular example, I can say that the value that I'm trying to look for can lie between 11.59 and 12.01 inclusive. So we see that this value means that my experiment was actually very accurate and it was on point. So the way we find this absolute uncertainty, as mentioned before, is sometimes equipment will state the absolute uncertainty. However, if we don't, and we have a ruler like this, the uncertainty is half the increment. So you see here, we go in millimeters. So 1 millimeter is also 0.1 of a centimeter, and half of that is 0.05. So that will be our uncertainty, as this is the increment. So let's say, going back to the earlier example, we put 2.41, I believe, and we have the plus or minus 0.05. So if you remember, we wanted to put 2.409, maybe because we thought that was more accurate, but we can only have one uncertain digit. Well, because we have this uncertainty, we can say that this is in the range of where of the measurement of the bone, and thus, since this is included with this range, we can say that basically, even if we do think this is the proper measurement, uh, this actually suffices as it includes this within its range. So the second point to consider is, what if I'm using a scale and there's a digital readout? Would that mean that there's no uncertainty? Well, in the case of digital readouts, the uncertainty is the value of the last decimal place. So the uncertainty here, since we go to 0.00, and this is the last digit, we say that 0.01 is the uncertainty. So, as explained earlier, this allows us to see if two measurements are consistent, namely our 2.41 and our assumed 2.409, though this is not really accurate. If someone says 2.42, for example, which is a valid answer considering the uncertain digit, we say that this is still consistent with this previous result, and we say that this is reproducible. As if person A got this and I got this, and our uncertainties overlap, basically we can say that these experiments are basically, in a sense, consistent. Let's say you have plus or minus 2 meters, and you're only trying to measure your room, then this uncertainty would be too large, because a room itself, at most, maybe if it's just your bedroom, can have 5 meters in width. That's being generous, and that's so close. This means the instrument and the way you're measuring your room is imprecise and possibly inaccurate as well. So if you have an experiment with such a large uncertainty value, it should be noted and possibly written somewhere. So just quickly, let's review on significant figures. There's just two quick rules. There's a few more, but these are things to go by. So all whole numbers are significant digits, except for trailing zeros. So for decimal numbers, all whole numbers are significant, including the trailing zeros. So if I had 250.0, you say that you say that this value is a significant figure. However, if we did not have this decimal, this is not a significant figure. And another thing to note is that leading zeros do not count as significant figures. So, in a given example of, let's say, 5,000, since trailing zeros are not significant figures, we only have one sig fig. Let's say we have something like 1.0702. Well, since there's no leading, leading zeros, since this is a 1 and this is not a 0, we say that there is 1, 2, 3, 4, 5 sig figs. And this applies to scientific notation as well. If we have something like 1.000, and note that since there is a decimal, these are not trailing zeros, so these are 4 significant figures. You can say that this has 4 sig figs, as this does not count as a sig fig. So an important thing to note is that sig figs are only used in measurements. So all of these have to have a unit. Defined values or counted values do not have significant figures. So if I see 5 sheep, let's just say I see 2 sheep since it's hard to draw, and they both weigh, let's say, 55.62 kilograms. Let's just say we have plus or minus 0.1. And I see two of them, so I want to get the total weights. This does not have a significant figure as it's counted. So we do not have significant figures for counted or defined values. And defined just means that it already has a value unique to it. So maybe we can talk about pi. So if we just have pi and we want to multiply for some reason, we don't need significant figures for it. So let's go back to the top. For significant figures, if we have addition, what we want is the minimum number of decimal places in the answer. So since these both have 2 and 2 is the lowest, put 2. However, let's say we also wanted to add 1.5. Then, since 1 is the least amount of decimal places, we will only put 1. So this will be 306.5. And since these are equal to 3, we don't want the 3 as we round it to 1 decimal place. So if we are multiplying significant figures, we keep basically the least amount of significant figures instead of decimal count. So this one has 5, this one has 1, so we want our answer to only have 1. So this would be just 400. If you're still wondering why, this will be 205 times 2, 410.02. And since we don't want anything after the first one, we round this. And since 1 is less than 5, we round down to 400. And note that this only has 1 significant digits and 2 trailing zeros. So let's continue on with adding and subtracting uncertainties. So if let's say we have 205.01 plus or minus 0.05, and we wanted to add this to 100.02, also plus or minus 0.05. As you can see, this uncertainties make the equation fairly long. We see we always add the 2. Even if it's subtraction, we still add the uncertainties, as this is basically the range of uncertainty. So the range of values that the experiment could be, not is, by the way. So since we're adding uncertainties, we want our final uncertainty to be the sum of the previous two. So that's plus or minus 0.1. And since we're adding, make sure the significant digits are consistent. So, and then we just put 305 point, let's see, 0.3. That's our final answer. So what happens if we multiply numbers with uncertainty? Well, there's 2 case scenarios. The first one is with a number that doesn't have uncertainty. Note that this could be maybe a counted value, like the sheep from before. What we do is we simply multiply the uncertainty by the number as well. So this turns into 410.02 plus or minus 0.1. However, the second case scenario, let's just make the numbers a bit more manageable. 10 plus or minus 0.05, and we want to multiply that by, let's say, 2 plus or minus 0.05. So what we do here is we want to convert these, oh my bad, into percentage uncertainty, which is also called relative uncertainty. So relative uncertainty is equal to the absolute uncertainty over the measured value. Please note that this is in percent form, so we have to multiply this by 100. So in this scenario, we put 0.10 plus or minus, and then we do 0.05 over 10, multiply that by 100, and we put a percent sign, and then we do the same here. For the first one, we get plus or minus 0.5%. For the second one, we get 2.5%. So what we do now is, no matter if it's division or multiplication, we add these values together, and we just multiply these. So this turns out to be, note that this has 3 significant figures, and since it's multiplication, we want the least. So this turns into 20.0 plus or minus 3%. That will be with. Since it's addition, we keep the decimal case. However, this is never the final answer, as we always have to remember to convert this back into an actual value from the relative uncertainty. So we just multiplied the 3 divided by 100 to get the decimal, and multiply that by 20 to get our final answer. And that will be 0.6, and then we just put our units. So intuitively, you can see that if if we were just bringing this to, let's say, the second power, just this, we will be just adding 0.5 and 0.5. So the number of times we multiply it is the number of times we add the uncertainty. So when you bring something to the power of n, you multiply the percent uncertainty by n. And similarly for square roots, or any type of roots, you divide it by n. So to finish off today, let's just, since we're running out of space, start here. So this is our final thing, and that is percentage error. So percentage error is basically the precision of our experiment. compared to earlier where we were talking about the accuracy. So our experimental value is basically the one we get from the experiment of which we measured, and we want to put it over the literature value. So we take intuitively the percentage error is equal to the literature value minus the experimental value over the final experimental value. The final literature value, or the one from the beginning. And this is in percent form, so we multiply everything by 100 and give it the percent. So what you might be asking, where do we even find this literature value that we talked about earlier, all the way here? Well, two sources that are commonly used are the CRC, Handbook of Chemistry, and the NIST Chemistry Webbook. And basically, you can find a lot of published values, usually recognized by most scientists. These are the accepted values in the scientific community. And just for practice, maybe using all of the lessons learned, here is the problem for you to solve at home. So let's say there's a cone. Let's say, since this is HL chemistry, let's make this a bit harder. Let's say the radius of this cone is maybe like 5, plus or minus 0.5 millimeters. And let's say this slant over here is, let's see, what's a good number? 8.3 plus or minus 0.5 millimeters. So the goal is to find the volume and express your final answer with the correct sig figs and the correct uncertainty. Anyways, that is all for today's lesson. Thank you for watching, and I hope episode 2 will come along soon, though there are a lot of other subjects coming, maybe French, math, and the ultimate goal of this channel is to really help IB students across the world learn some subjects maybe through the perspective and the eyes of another student. This might be not the most accurate or most well executed video, however, I hope from student to student, I have facilitated the learning process and maybe explained at least in a way of which I would understand. So hopefully you too have gained something valuable from this episode. Again, this is 52